Okay, in previous class, we had a discussion about molecularity of the reaction, right? So, as you know that a chemical reaction that takes place in only one step, what we call elementary reaction, right? So, chemical reaction takes place in only one step. That is what we call elementary reaction. This takes place in multiple steps. Simply what we call the two or more steps. It means it is complicated reaction or else complex reaction, right? Into what we call complicated reaction or else complex reaction. Am I audible properly? Yes or no? Hello?
Yes, sir.
Okay, fine. Okay, so if we consider the molecularity of the reaction, we can define for only for elementary reaction, right? Elementary reaction. Here, sequence of steps through which complicated reaction takes place, what we call mechanism, right? So each step in a mechanism we should consider as elementary reaction, right? Each step in mechanism, okay, or else complex reaction we should consider as a elementary reaction. Okay. For elementary reaction only, we can define the molecularity of the reaction, right? According to this, the molecularity of the reaction is nothing but what is defined as a minimum number of molecules or atoms or ions that taking part in the chemical reaction, right? Balanced chemical reaction, right? So, in general, what we call molecularity of simple reaction is equal to sum of the number of molecules or else molecules of reactants involved in the balanced chemical stoichiometric equation. And here the definition: number of atoms or ions or molecules taking part in lowest step, that is rate determining step, called molecularity of the reaction. We always define the molecularity of the reaction for rate determining step only. Okay, rate determining step nothing but slowest step of the reaction, right? Slowest step of the reaction. We cannot predict the molecularity of the reaction with respect to fast reaction, right? With respect to fast reaction, that is not a rate determining step, right? It is not a rate determining step. Got it? So we can define only for slowest step of the reaction. So slowest step nothing but what? Rate determining step, right? Rate determining step. So these are the example here to decomposition of PCl5. So here the only one molecule is involved, right? One molecule is involved. So that is a unimolecular, right? That is unimolecular. So, and remember one thing, the molecular reaction we can define with respect to reactants only, not with respect to product. So with respect to reactant only, we have to consider. So, and we just look at the coefficient also, nothing but a stoichiometric coefficient. So that is attached with respect to reactant, right? So here the two HI, nothing but two molecules of HI, right? Two molecules of HI. So use H2I2, which means what is the molecularity here? Molecularity, just tell me.
Bimolecular.
Bimolecular, right? It is bimolecular. Similarly, here two molecules of SO2 reacts with one molecule of O2. Okay. With respect to reactant, so what is the molecularity here?
Trimolecular.
Trimolecular, right? Trimolecular. These are very simple. Here also one NO and one O3. So which means bimolecular, right? And here two CO and one O2. So which means trimolecular. And one more thing. So two FeCl3 react with one SnCl2, which means trimolecular, right? Trimolecular. And some special, we consider some special case here, that is decomposition of H2O2. It can take place by means of two steps, right? So this is the overall reaction. So in first step, what happens? Look at this carefully. So production of nascent oxygen, right? H2O2 gives H2O and one nascent oxygen. Then that is slowest step of the reaction, right? Slowest step of the reaction, nothing but a rate determining step. Okay, in the sorry, step two. This is step two, and this is step two. Two nascent oxygen combines to form O2, right? Two nascent oxygen combines to form O2, and this is fast reaction. Fast reaction. And now tell me, for fast reaction, we can define the molecular reaction. Is it possible? Is it possible to define the molecular reaction? Yes or no? Yes. Anybody else? Is it possible to predict the molecularity of the reaction for fast reaction?
No,
Can you
sir.
hear? Yeah. So why? Because here velocity of fast reaction we cannot find out, right? So according to first step, that is unimolecular only, right? In this reaction, according to first step, that is unimolecular only. Here. So here the molecularity is nothing but a theoretical concept. As you know that molecularity cannot be zero, negative or else fractional. It is always whole number, right? Molecularity cannot be a zero, negative or else fractional. It is always whole number, right? It is infinite and imaginary. Molecularity cannot be greater than 3 because more than 3 molecules may not mutually collide with each other. So, according to collision theory, maximum 3 molecules can collide at a time, right? So, molecularity cannot be greater than 3. Okay. So, for example, here look at this. Here the 4 molecules of HPR are there, right? Then 1 molecule of O2. According to reactants, so 5 molecules are involved, right? 5 molecules are involved. So, according to collision theory, what we say, molecularity cannot be greater than 3, right? Why? Because more than 3 molecules may not mutually collide with each other, right? So, we can consider the complex reaction. This one is we can consider the complex reaction. So, for complex reaction, we have to predict the mechanism, right? We have to predict the mechanism. And you know that each step in a complex reaction, we could consider the elementary reaction, right? So, molecular reaction uh, we can define with respect to elementary reaction, right? So here, first step. This is the first step, and according to first step, that is bimolecular, and here the second step, according to second step, that is also a bimolecular, right? And this is third step. According to this, that is also a bimolecular. Okay. So in this way, we have to define the molecularity of the reaction with respect to complex reaction, right? With respect to complex reaction. Okay, and difference between the molecularity and order of the reaction we could consider here. So molecularity, so it is nothing but what total number of reactant species, nothing but molecules or atoms or ions which bring the chemical change, right? So we just consider total number of reacting species. So nothing but molecules or atoms or ions, right? But order of the reaction, what we have to consider sum of the powers of molar concentration, right? It's nothing but what sum of the powers of molar concentration of the reacting species in rate equation of the reaction, right? Rate equation of the reaction. So it is always whole number, nothing but molecularity is always a whole number. So what about order of reaction? So it may be a whole number, zero, or else fractional, right? It may be a whole number, zero, or else fractional. Okay. So molecularity is nothing but it is a theoretical concept, right? It is not a practical approach. It is a theoretical concept. The order of the reaction we can determine experimentally. Okay, we can determine experimentally, but it is also experimental concept, right? So molecularity it is meaningful only for simple reaction, whereas individual step of the complex reaction, right? It is meaningful only for simple reaction or individual step of a complex reaction. So it is meaningless for overall reaction, right? It is meaningless for overall complex reaction, right? So here, in case of order of reaction, it is mean for a reaction, whole reaction, right? Not individual step. It is mean for whole reaction, not for individual step. Got it? This is about molecularity of the reaction. So today we have to discuss one more important concept. I think all of you know that zero order reaction. Okay, shall we discuss about this zero order reaction? And now tell me what is zero order reaction? The name itself indicates zero order reaction. What it means? Anybody else? Order of the reaction, you know that the rate of reaction depends on what? The concentration of the reactant, right? Simply what we call concentration of the reactant, right? Here, zero order reaction is there, right? Can you define what is zero order reaction? Anybody else? Can you hear me? Hello? Can you hear me?
Yes, sir.
Yeah, tell me then. Zero order reaction means what? A very simple definition we have. Zero order reaction. Order of the reaction means what? If the rate of the reaction depends on one concentration term, so that is first order. Second means second order. Two reactants means second order, right? So here we have zero order reaction. Okay? Can you define according to that?
The rate of reaction does not depend on concentration of the reactants.
Yeah. The rate of the reaction does not depend on concentration of any reactant. Simply what we call does not depend on concentration of any reactant, right? Means is independent on concentration of the reactant, right? Here the reaction is said to be a zero order. Okay, a reaction is said to be a zero order if the rate of the reaction is independent on the concentration of the reactant. Got it? The rate of the reaction is independent. Got it? Independent on the concentration of the reactant. Right. So that is what we call zero order reaction. Clear? So the rates of zero order reaction, the point should be noted, the rates of zero order reaction do not vary with respect to increasing or else decreasing concentration of the reactant. As you know that reaction is going on, which means concentration of reactant going increases or decreases. You know that, right? So, but in case of zero order reaction, the rate zero order reaction, and here is not vary with respect to increasing or decreasing the concentration of the reactant, which means it remains constant, right? Constant means the concentration remains constant, right? Concentration of the reactant remains constant. That is what we call zero order reaction. It should not vary with respect to increasing or else decreasing the concentration of the reactant. So it should be constant in the sense what we call that. What about the rate of reaction in this case? Rate of reaction that is equal to what? This constant means what? Simply what we call this means the rate of the reaction is equal to rate constant. Is K, right? Which means the rate of the reaction is equal to rate constant K of that reaction, right? Of that reaction. Simply the rate of reaction that is equal to K only. That is equal to K only, right? So here, according to this, a reaction in which rate of reaction does not depend on concentration of the reactant, then we have to just call it as zero order reaction, right? Reaction in which rate of reaction does not depend on concentration of the reactant, so that is called zero order reaction. Okay, so just tell me one example for that zero order reaction. Just think about concentration independent. Any example for that? Anybody else want to give? Anybody else? Rate of the reaction does not depend on concentration of the reactant. Can you hear me? Can you hear me?
Yes, sir.
He's talking. Tell me any example for that. Meenakshi,
Yes, sir.
any example? Can you give?
Sir, I'm thinking, sir.
Anybody else? Okay, look at this. Can you see my screen?
Yes, sir.
Can you see? So, what is that reaction? What is that reaction? Decomposition of ammonia, right? Decomposition of ammonia with respect to a catalyst surface. Decomposition of ammonia on the surface of the catalyst. So, what is the catalyst here? W, which means what? Yes, tell me. W means what? Metal catalyst only. Which metal it is? Which metal it is? W means what? Can you hear me?
Tungsten.
Yeah, tungsten only. Okay. Here the decomposition of ammonia on the surface of this tungsten. So that is what we call example for the zero order reaction. Can you justify this one? How does it does not react? Does not depend on the concentration of the reactant. So reactant nothing but here the gaseous molecule, nothing but ammonia only, right? Ammonia only. The decomposition of ammonia is a gas, right? Gas molecule, right? Gas molecule, and according to zero order reaction, so we just say that is not depends on the concentration of the ammonia, right? Concentration of ammonia molecule. Can you justify this? How does it does not depends on concentration of ammonia? Okay, get this. So according to this, simply what we called rate, that is equal to K, K into concentration of ammonia. Can mention zero only. Why? Because it is not depends on concentration of ammonia. I will tell you later why. So here, according to zero order reaction, the rate of the reaction that is exactly equal to constant, nothing but K only. K. That is does not depends on the concentration, initial concentration of ammonia, right? Initial concentration of ammonia, which means the reaction is said to be a zero order. The rate of the reaction is independent on the concentration of the reactant, right? So independent the concentration of the reactant means here also. So we have to take an ammonia, right? That is independent on the concentration of the ammonia only, right? How? But how? That is the question, right? So look at this. First case, what happens? The gaseous molecules of reacting substances get absorbed on the surface of the catalyst, right? That is what we call adsorption phenomena, right? Adsorption phenomena. So first thing what happens in first case, the gaseous molecule of reacting substance get absorbed on the surface of the catalyst. That is the first process. So that is nothing but initial molecule, ammonia molecule get absorbed on the surface of the catalyst. So on the surface of the catalyst means what? On the surface of the tungsten. So here the catalyst is tungsten, right? So what happens then? Surface is thus fully occupied with the molecules of reactants. Okay, the surface is thus fully occupied with the molecules of the reactant. Some of these molecules react to form product. Okay, some of these molecules react to form product, but immediately new molecules takes up their position, and thus the concentration of the reacting species remains constant on the surface. Okay, so point should be careful. Note, you just note this point carefully. So some of these molecules react to form product, but immediately new molecule takes up their position, and thus concentration of the reacting molecule remain constant with respect to surface. Okay, with respect to surface of the catalyst, the molecules come and react to convert the product. Again, new fresh molecules they get absorbed on the surface of the metal, and surface of the metal nothing but tungsten only. Again, they have to convert into product. So at the surface, just consider not whole reaction. Okay, at the surface, just consider at the surface the concentration remains constant. Some are comes, some are out, right? Like that. Some new molecules comes, get absorbed on the surface of the catalyst, then it is converted into product. So the concentration remains constant at the surface, right? And hence the rate of the reaction remains constant irrespective of the total amount of the gaseous reactant taken initially. Okay, and this is the best example for zero order reaction, right? So here the concentration independent, right? Simply what we say, concentration independent, right? And look at this image carefully. Overall process we can show like this. So here some of NH3 molecule initially get absorbed on the surface of the catalyst, and it is converted into a respective product. Again, new molecules comes, get absorbed at the surface, again go with respect to convert the product, right? So just consider the surface. Surface, just consider the concentration remains constant. Okay. With respect to surface of the catalyst, could say the concentration of the reactant is constant, does not change, either decreases or increases like that. It should be a constant, nothing but it remains constant. So that this is the best example for zero order reaction, right? Okay. So now we can consider the mathematical expression for zero order reaction. Okay, mathematical expression for zero order reaction. So if A is the initial concentration, the expression for the rate of zero order reaction may be written as follows. And look at this: dx by dt, nothing but rate of the reaction is directly proportional to initial concentration, right? So zero represents concentration independent. Got it? Zero represents the concentration independent with respect to reactant. Okay. Here the rate of reaction is directly proportional to initial concentration, right? So dx by dt. Then dx, or else we can rearrange this equation. Dx by dt, that is equal to k, right? Dx by dt, that is equal to k, nothing but rate constant. Okay, zero order in the sense rate of reaction is nothing but constant only. Okay, rate of reaction is nothing but rate constant. So with respect to zero order reaction, right? So where k is the rate constant for zero order reaction. Yeah. The above expression may be written as dx, that is equal to k into t. Just rearranging this above equation, this equation, right? Just rearranging this equation. That is dx, that is equal to k into t, right? K into t. So integrate this equation, we get integrate this equation. What we get then? Just integrate this equation. Integration of dx and integration of this one. What we get? Tell me. Yes, integration of dx. Integration of dx. Can you hear me? Can you hear me?
Yes, sir.
Yeah, integration of dx. What do you get then? You forgot?
Equals to KT.
So here x is equal to integration of dx, nothing but x only. So here integration of k dt, right? So kt plus I, right? Kt plus I. So what is I? Nothing but integration constant, right? Where I is nothing but integration constant, right? So if you want to know the value of integration constant, you want to know the value of integration constant, just put this nothing but t is equal to 0 and x is equal to 0 to that equation. Then you have to find out the value of I, nothing but integration constant. So if you put t is equal to 0, so this term, right, this term, nothing but kt becomes 0, right? If you put x is equal to 0, so that is also becomes 0. And value of I is nothing but, value of I nothing but 0 only, right? Value of I nothing but 0, 1. Okay, put the value, put the value in equation only, then you will get x is equal to kt only, right? X is equal to kt only. So correct as equation number 1. X is equal to kt only. And this is the mathematical expression for zero order reaction. Okay, this is the mathematical expression for zero order reaction. X is equal to kt, and this is very important. Again I repeat, okay, x is equal to kt, that is the mathematical expression for zero order reaction. Got it? Okay, now we just consider one more concept, that is half-life period. Half-life period, the name itself indicates what is that half-life period. Half-life period, T half. What it indicates? Any idea?
The time taken for half of the substance to
Yeah,
decompose.
exactly. So it is the time required to convert half of the initial concentration reaction into product, right? It is the time required to convert half of the initial concentration of the reactant into product, right? So or else the time taken for half of the reaction to complete, right? Time taken for half of the reaction to complete, right? So if you want to know the half-life period for zero order reaction, just consider this when x is equal to a by 2. So A, you know that initial concentration, right? So now we are going to find out half-life period, right? So just put the condition here, x is equal to A by 2. So half of the initial concentration of the reactant consider, right? So then T is equal to T half, right? X is equal to A by 2, then T is equal to T half, right? So then equation 1 becomes, so x nothing but what? A by 2. As you know that expression for zero order reaction nothing but what? X is equal to KT, right? X is equal to KT. So for half-life period, when x is equal to A by 2 and T is equal to T half, so what we will get? A by 2 that is equal to K T half, right? K T half. So we want T half now. Take it outside. T half that is equal to what? T half that is equal to what? A by, tell me, A by, anybody else? A by, what is that? Can you hear me? Can you see my screen?
2K.
Yeah. T half that is equal to A by 2K. Okay. So this is also very, very important. So they will ask problems with respect to half-life period for each reaction, means zero order, first order, second order, like that. And this is half-life period for which one? Is it first order? Is it first order?
Zero order.
Zero order, right? So then what is the expression for zero order reaction? X is equal to KT, right? Expression for zero order reaction that is equal to X is equal to KT. So half-life period for zero order reaction nothing but what? T of that is equal to A by 2K. Got it? A by 2K. Clear? And this is the half-life period for zero order reaction. And now we just move on to the next concept, that is first order reaction. Now tell me, zero order means what? Zero order means concentration independent. So first order means what? First order means what? The rate of reaction is, yeah, tell me, depends on what? Yes, rate of reaction is depends on what? Concentration of, anybody else? Concentration of, yes, tell me.
Reactants.
So how many? How many reactants? Is it 1 or 2 or 100?
Both the reactants.
First order, right? The concentration of the, sorry, rate of reaction depends on concentration of only one. Yes, tell me.
One reactant.
Exactly. The reaction is said to be a first order if the rate of the reaction depends on one concentration term only, right? One concentration term, nothing but only one concentration, right? Only one reactant, right? Only one reactant. A reaction is said to be a first order. The rate of the reaction depends on only one concentration term, or else only one reactant. Clear? So let us consider here A is nothing but only one reactant we have, right? That is not A plus B, that is A only, right? So A nothing but only one reactant we have. So that reactant is going to convert into product, right? So that is the general type representation of first order reaction, which means only one reactant is going to convert into product. Nothing but the concentration depends on only one reactant. Here, according to this, so A is nothing but what? Initial concentration of the reactant. Okay, A is nothing but what? Initial concentration of the reactant. So after time t, so change in concentration we can represent with respect to x. Okay, after some certain time t, nothing but after time t, the x is nothing but what? Change in concentration. Okay, change in concentration, that is also represented in terms of moles per liter. Okay, so after time t, so we can represent the concentration of the reactant. Concentration of the reactant after time t is given by T is equal to A minus X, right? T is equal to A minus X. A is the initial concentration and X is the change in concentration with respect to time, right? Right, with respect to time. So after time T, the concentration of the reactant is given by is T is equal to A minus X. T is equal to A minus X. Okay. Then according to law of mass action, if the rate of reaction is defined as rate of reaction is defined with respect to first order, that is A minus X. A is nothing but what? Initial concentration, and X is nothing but what? Change in concentration, right? Rate of reaction is directly proportional to concentration of the reactant after time T. So here after time T, the concentration of the reactant is A minus X, right? After time T, the concentration of the reaction is A minus X, which means the rate of the reaction, nothing but dx by dt, that is directly proportional to the concentration of the one reactant. We have only one reactant, right? That is nothing but A minus X here. A minus X here. So just rearrange this equation. Dx by dt, that is equal to K into A minus X, right? K is nothing but what? A rate constant, right? Dx divided by dt, that is equal to K into A minus X. That is rate constant, right? Cartesian equation number 1. Okay, where K is rate constant. So equation 1 may be rewritten as, that is dx by A minus X, that is equal to K into dt. Okay, dx by A minus X equal to K into dt. Cartesian equation number 2. So less than 1 minute is there. Just rejoin with the same link. Got it? So here the dx, that is equal to, sorry, dx minus A minus that is equal to K into dt. Cartesian equation number 2. So then what are you going to do now? Yes? Anybody else? Same thing you have to follow with respect to zero order reaction.
Integration.
Integration, right? So integration, so with respect to dx by A minus X, and integration with respect to K into dt, right? What you will get then? Integration of this dx by